Hi, I'm Hayden, an engineer here at 4DSP, and today I wanted to give you an overview of the 4DSP board support package. So I'm going to break this up into two pieces. I'm going to give you a quick introduction of the BSP and some concepts and components that are included therein, and I'm actually going to give you a live demo of the FPGA tools and some of the host tools. So first let's start with an introduction. 4DSP has really kind of three different ways that pieces of our business, and so we're very well known for our FPGA mezzanine card, or FMC boards, but an FMC board by itself is not particularly useful. It has to be paired with an FPGA carrier card. So our FMCs can be supported on a number of FPGA carrier cards. We have many FPGA carrier cards in the 3U and 6U VPX, PCI Express, XMC, and in our compact embedded system series products. Those combined together, we ship with a board support package, which we'll go into the details here in a moment. And the standard board support package has some basic functionality to get you up and going. Above and beyond that, we would employ some of our engineering services to give a more advanced board support package for some application-specific IP or some very particular requirement for your application. In our engineering services section of our business, we can also do custom board modification to existing designs, even to design from the ground up new PCB designs for your particular application. Taking those products and integrating them into a off-the-shelf platform with third-party components, we do integrated solutions. An example of this is our VPX167 airborne platform pod based on our VP780 in a 3U VPX form factor. And so these are systems that are delivered as kind of more turnkey solutions where customers can integrate their application-specific IP into a larger system. But common to each of these systems is a common architecture. And I kind of call this the COTS, or consumer off-the-shelf platform architecture. And this is, in each system really has, it's common to all FPGA systems, is a processor, FPGA, and I/O. Now we take the approach of having open standard interfaces like the VITA571 defined FMC interface and OpenVPX, which is also defined by VITA. We also support things like PCI Express and form factors like our compact embedded system, all programmable with standard off-the-shelf tools like Xilinx Vivado or ISE. And so the board support package comes really with three components here: host tools, FPGA tools, and diagnostic tools. And so starting in the middle, the FPGA tools that we provide are something called Stellar IP. And so the BSP is one big installer, and you get a license file. It installs everything included within the BSP. And on the FPGA side, Stellar IP is the IP integration design flow assistant that accompanies our BSP. And this is a tool that will auto-generate a top-level VHDL reference design, constraints generation, etc. We'll go into more detail here in a moment. On the host side, we provide open source C and C++ reference examples supporting a number of operating systems. And on Windows, we have a graphical user interface diagnostic tool called 4FM that does some basic tests to make sure your boards are up and running when you get them out of the box. So at 4DSP, we are some cosmology enthusiasts, and so within Stellar IP, we have a couple terms I want to highlight here. The term star within the context of Stellar IP is really just an IP block, or a DSP block, or an interface, I/O interface block. And these are interconnected through either a basic command bus or a data streaming bus like AXI, for example, and we kind of call these wormholes. And multiple stars built into a top-level reference design we call a constellation. And you'll see how this applies here in a moment whenever I show you some of the documentation. And so Stellar IP, you have a top-level constellation, and it'll output a Xilinx top-level project, either in ISE or Vivado, and it's a top-level VHDL reference design, design synthesis scripts, design constraints, and a number of other benefits. It also auto-generates IP block control address offsets. All these things are the pieces of a design that tend to be very error-prone. And so at this point, out of Stellar IP, you may only need to use it once, auto-generate your Xilinx project, and you're off and running within Xilinx. Tools like ISE or Vivado. So the compact embedded system product line is what I'm going to show you a lot of demos here today, and I just want to highlight what this is. This is a processor, FPGA, and I/O all in a very small form factor. So here on the left is a CES 720, which has a, as you can see under the hood, it has a VITA-57.1 compliant FMC module. So here on my desk I have a compact embedded system, and over here on the right is an air-cooled CES unit. Within this compact embedded system I have an FMC 150, which has 2 A to Ds and 2 D to As that you can see I have connected to loopback. Over here on the left is a CES CC820, which is a rugged conduction cooled version of the exact same processor, FPGA, and I/O hardware. So here in the air-cooled version, you can use this as a lab development system, so you can go quickly from development to deployment with a rugged conduction cooled version, all on a common platform. So let's take a look at the board support package for this particular compact embedded system I have here at my desk. So here in Windows, we can go to C drive, program files, 4DSP. There's 4 directories here. Let's look underneath common. You'll see firmware, and I have a lot of .4ff files here. So let me maximize this window. And these are files for a lot of different combinations. You can see we have VC707s and an FMC230. There's one in particular here, Constellation ID. So this number is a firmware ID or Constellation ID. And let's look at Constellation ID 450. So this 4FF file will extract the complete firmware reference design. So you can kind of think of this 4FF file as like a zip file, if you will. And so it extracts to an extraction directory. And here you can see I have 3 Stellar IP design files. So if I go ahead and open up the 150 with the 410 FPGA and Stellar IP, which I already have open here, you can see I have a top-level IP design in a graphical tool, which this is Stellar IP. So you can see I have 9 IP blocks. I'm going to take a look at some of these IP blocks. So let's look over here on the right. This is the host interface, and this is a PCI Express IP core. An IP core like this could cost upwards of $30,000 from a third-party vendor. We have in-house developed this IP core at 4DSP, and it's included with the board support package for free. So this particular IP core, you can see, has a couple things: a command bus, commands going out, commands coming in, and a data bus coming out. And so the data coming out of this particular IP core goes to this block over here, which is a data router. And so this routes from 1 data input to 3 outputs. And so you can see that the bottom output goes to a 3-to-1 data router that goes right back to the host interface. So you can kind of do a little data loopback to test your data path if you wanted to with this reference design without even talking to the FMC. So out of this data router, you have 2 channels that go to this module up here, which is the FMC 150 IP block. And so it has 2 DACs and 2 ADCs, and so the data comes from the host right into the DACs and from the ADCs right back into the host. And this abstracts all the data bus interfaces on the FPGA. And one thing I wanted to highlight, if you go back to our firmware file here, you can see that there's a directory called doc, and under doc there's this CD or Constellation Document 450. And within this constellation, it's a reference firmware for the CES unit. And you can see this has a lot of information about each of the IP blocks, how they're interconnected, but it doesn't have a lot of details about what each IP block does, in terms of programming that IP block. If we go back into Stellar IP, you can right-click on a particular IP block and open documentation, and this is a star document, and you can see by the SD number notation on the particular IP block. So we have a large library of stars or IP blocks that you can leverage within your design. And so this has a lot of information baked into it that has like the register map and various different control offsets for and bit descriptions for various registers within this IP block for controlling the FMC unit. And so from this point, we have the final IP block I want to highlight is this Constellation ID block, and this has the ID, that number 450 is baked into this, as well as a number of other FPGA build identifications and memory offsets. And so from here we can take this top level Constellation or reference design and auto generate a Xilinx ISE VHDL top-level design. So we can go here at Stellar IP, we can hit Generate, and we can see that we're generating a top-level design here. It's instantiating some tools, and shouldn't take too long here. And you can see that the auto-generation of the top-level design is complete. And so we can go back into our firmware, our extracted firmware design, and you can see there's a new directory here called Output. And underneath here you can see we have an ISE project. And so we auto-generated the ISE project. Let me go ahead and open this up in Project Navigator. And there's a couple things going on here. There's a top-level design that has all the pin signal definitions. And we can look down underneath this project and we can see that there's a .ucf file that defines which pin on the FPGA that signal is connected to. And that's, you know, pretty standard stuff for FPGAs, but it's auto-generated by Stellar IP. And so at the top level, you can see that there's a number of signal definitions and component definitions, as well as an instantiation of a top-level reference design that was auto-generated by Stellar IP. So here's that one interface we were looking at, the host interface. And there's a lot more wires here or signals connected than were shown in Stellar IP. Well, that's because it was aggregating these buses into what we call a wormhole to simplify the top-level architecture. But here you can see that the data bus that we were looking at comprises of 3 signal names: a data bus, a stop, and a data valid line. And so these can be a number of different interface protocols like AXI. And so from here we can take our reference design and generate a bit file, download it to a flash, or download it to our FPGA through a JTAG interface connector, through Impact or Vivado hardware manager, and at that point our FPGA is configured. And so in that point we can move over and take a look at the CES unit on the host portion of the board support package. So I have a compact embedded system here, and so I'm going to remote desktop into the unit here because I'm running Windows on my CES unit. So if we have the BSP installed here, and so I can go to C drive, program files, 4DSP, and under these 4 directories, let's look under the FMC board support package, because let's take a look at the FMC 150 we have on this unit. And under here you can see we have a document called a folder called refs software, and since we have an FMC 150, let's look at the FMC 15X app. So this is a pre-built Visual Studio application, and so here I already have this opened in Visual Studio Express, and this is a kind of a high-level reference design console application. So it's a basic command line application, and so it'll do some basic functionality for your FMC 150 just to make sure everything's up and running and give you an example of how to program it. So let's go ahead and run this application. So as it's compiled and run here, you can kind of see a number of things are coming across the console. So this is a basic console application. If you're familiar with C, this is a very common architecture of code. It's not intended to be particularly advanced. But again, we see that Constellation ID 450. We queried that, and it detected there's 9 stars in that bit file that we downloaded to our FPGA. We have a software and firmware build ID. We are able to query some voltages, configure the clock VCXO, lock the PLL, do a training sequence on the digital lines, set up some clock dividers to get to a particular ADC and DAC frequency. You can see here we're at 245.76 on the ADC and 122.88 on the DAC. Those are all based on a 491.52 VCXO that was included on the board. And once all that's up and running, we do some basic digital pattern checks on the ADCs and DACs to make sure that the digital lines are working appropriately. And you can see here that the pattern passed, so we're pretty confident this is connected up correctly. And so from there you can go in and see that there's a number of APIs and libraries here. So for particular, we'll have an API, a header file for the ADC, for example. You can see here there's an initialization function, that pattern check function that we saw run, some read and write register functions within this API. And so there's a different API for different functions on the board, like the clock tree, the ADC, the DAC, etc. And so the intention here is that you will be able to take this as a starting point, a known functional example, and know how to program your FPGA-based system with your 40SP, either your 40SP FPGA-based system with your 40SP FMC module on it. And so the third and final component to the 40SP board support package is in Windows is some diagnostic tools, which is this 4FM graphical user interface. So I'll go over that briefly right here, but essentially this is just a utility that we install with the board support package in Windows. It just gives you some basic diagnostic information. So I can connect this up to my CES unit here at my desk. And you can see I'm going to get a number of tabs that are open. We can do things like basic memory tests, just query the boards, and things of this nature. And so here you can see, again, it queries the board. We see the FPGA device type right here and the firmware ID. And so there's a number of different test functions, but I'm going to show you this FMC analyzer because I have an FMC 150. So I can open this up, and I can select, I have an FMC 150, I'm using a CES 720, it's a PCI Express interface, and I can go ahead and make that connection to my FMC module within this GUI. Now these use all the same APIs that are that were under the hood that we saw back in the in Visual Studio, but now we just have a pre-built application around them. And so I can actually transmit out of my DAC or my and measure it on my ADC here. And you can see I have a nice CW tone, and it gives a little spectral display. And I can stop this, and I can also configure it for a different waveform type, a nice square wave, and I can look at this in a time domain view or a spectral view. And so there's just some basic diagnostic tool. This is by no means an advanced soft front panel, but it gives you just some basic functionality to know that your boards are working when you receive them right out of the box. And so the final thing I want to show you is back over here on my development system. If you go to C drive, program files, 4DSP, and look under the 4FM core development kit, you'll find a documentation directory, and there's a lot of documentation in here for the various different products that you may purchase. Some that are particularly useful is this 4FM Getting Started Guide or the 4FM Programmer's Guide, and this will give you a lot of information about the various different API calls that are included within the 4DSP host side board support package. So that's an overview of the 4DSP board support package. If you have any questions, feel free to reach out to us at sales@4dsp.com. Please visit our website to learn more about our advanced COTS, hardware, software, and system level products. Thank you for watching.